Okay, so second problem set. Remember that for the second problem set here, these are non-conservative forces, meaning that there's some external force from the system that is causing work to be done. So either adding energy to the system or removing energy from the system. So in this case, for these problems, it's no longer going to be initial energy equals final energy. It's going to be initial energy plus or minus work equals the final energy. That's what a non-conservative system would look like. So here we have a bin pushed across a horizontal surface. It's given an initial speed, and there's a coefficient of friction here. So use energy considerations to find the distance it moves before it stops. So in this case, we start off in my initial with a moving bin, V naught M. And in the end, this is my initial. And in the end, the bin is just stopped, right? V equals 0. So looking at my formula here, I would have E initial minus work equals E final. The reason I know it's negative is that I'm losing energy here. I'm going from moving or kinetic energy to not moving, no kinetic energy. That means the original kinetic energy minus the work done equals 0. Cool, cool? Remember that work is Fx cosine theta. And in this case, that force is the force of friction, X. And in this case, that cosine theta, because friction is a resistive force, that theta is always 180 degrees, which is what makes this negative work done. So in order to answer this question, I need to figure out what that force of friction is. That's equal to the normal force times mu. The normal force is going to be equal to the gravitational force. So frictional force equals m times g times mu. Going back to my original equation, I would have 1/2 mv naught squared minus m times g times mu times delta x equals 0, which is delta x, or the displacement, is equal to 1/2 mv naught squared divided by m times g times mu. Mass cancels, mass cancels, and you're left with delta x equals initial velocity squared over 2 times g times mu. For part B of this question, what would the stopping distance be if the initial speed is doubled? This question is probably most simply answered instead of actually doing calculations in terms of the meaning of kinetic energy, right? So we have the initial kinetic energy is going to be equal to the work done. That's simplifying this formula. So K naught minus W equals 0, or K naught equals W. And that's 1/2 mv squared equals force times delta x. Now in this case, force is constant. Delta x is equal to mv squared over 2f. Because force is constant, then doubling the velocity would quadruple the right side of this equation. Delta x equals m times 2v naught squared over 2f would mean delta x equals 4 m V naught squared over 2F. In other words, delta X is going to be 4 times the original value. Delta X new equals 4 times delta X original. So again, because velocity is squared in kinetic energy, doubling the velocity will actually quadruple the displacement when force stays constant. New problem here, we have a spring. So for part A, we're asked to start with the spring compressed, and then we are releasing it so that it passes through equilibrium, and we have a frictionless horizontal surface in the beginning here. Now, in a frictionless system, we have conservative forces. Initial energy is equal to final energy. Spring energy is equal to kinetic energy. So that's 1/2 kx squared equals 1/2 mv squared. 1/2 will cancel, and v will be equal to the square root of kx squared over m. So that's my first part here. Now, if there's friction, then the situation differs. With friction, we have non-conservative forces. So the initial energy plus or minus the work is equal to the final energy. And in this case, the work done is going to be negative again because friction removes energy from the system. So my starting energy will still be spring energy minus the force of friction times delta x equals 1/2 the kinetic energy at the end. I just got ahead of myself there. The final kinetic energy, or 1/2 kx squared minus f of friction times x. These are actually the same value, right? Because x is the distance from equilibrium. So that's also the distance that the spring will be pushing my object to get it back to equilibrium position, equals 1/2 mv squared. Force of friction again is going to be equal to the weight, so mg. I'm sorry. Force of friction is going to be equal to the normal force times the coefficient of friction, and the normal force is equal to mg mu. So we get 1/2 kx squared minus mg mu x equals 1/2 mv squared. That's kx squared minus 2 mg mu x over m. The square root of all that is equal to the velocity. Boom. And this is where these problems start getting a little more complicated. So here we have a student at the start of an incline, and they're going down this incline. So I'll draw it out. Here's my student at the top and at the bottom. So at the top, we're moving with some v initial. And at the bottom, we're moving with some v. Givens, I'm given v initial, I'm given v final, I'm given the height, I'm given the force of friction. I'm also given the length of this. I'm given the mass. And my question is, what is the work done by the student? So that means the student is exerting a force as well here. So we have friction exerting an outside force, and we have the student exerting an outside force as well. Presumably, friction's slowing the skateboard down, and the student is speeding the skateboard up by sort of pushing the skateboard along over this displacement as well. So one of the pieces of information that I'm going to need here is delta x, the hypotenuse of this triangle, which will be the square root of h squared plus L squared, where L is the length of the incline. Okay, so for this problem, initial energy plus or minus work is going to be equal to final energy. But in this case, there's two different forces doing two different amounts of work here. I have my initial energy here, minus the work done from friction, negative work, friction's taking away energy, plus the work done by the student. And all of that is going to be equal to the energy at the end. By the way, for some reason, it seems that my problem is a student on a skateboard and your problem is a child on a tricycle or something like that. They're the same problem, just different contexts for some strange reason. So at the top of this hill, my starting energy has gravitational and kinetic, moving and height, minus work done by friction plus work done by student equals, at the bottom, it only has kinetic energy. Coming back around here, and simplifying or expanding this further, we would have the mass of the student times g times the initial height of the student plus 1/2 the mass of the student times the initial velocity of the student squared minus the force of the friction times delta x plus the force of the student times delta x equals 1/2 mass of the student times the final velocity of the student squared. Sorry, just clarifying, it actually wants the whole work done by the student, so we can keep this as just work student. And then lastly, I'm just solving for that work student. So work student equals 1/2 mv squared minus mgh naught minus 1/2 mv naught squared plus the force of friction times delta x, where again that delta x is going to be the square root of h squared plus L squared. And that's my answer. Continuing on, now we work for the highway department. Hello, highway department. Thank you for hiring me in uncertain times, no less. So this is actually a cool problem, and I really like this context. You might have seen, if you've driven up and down from Tahoe, that there are these runaway truck ramps off the side of the freeway. They usually end up being like pretty long side roads that have gigantic piles of gravel on them. And the intent here is if the brakes of a big vehicle stop working, those are sort of escape routes that those trucks can crash into. And the piles of gravel will not stop the car instantaneously. They'll slow the car using friction over a larger distance. This is sort of like a conservation of momentum question in the concept of increasing the time it takes for the vehicle to stop decreases the maximum force that the vehicle experiences. So we have the mass of the truck given. the mass of the truck given, and we know the initial velocity of the truck is given as well. And we're given the coefficient of kinetic friction as well. So here, in this case, there's one additional confounding factor, which is that the truck is exiting at an angle. So here's my little escape ramp. It's at a theta of, in my case, 29 degrees. The truck's got some initial velocity going up the ramp, and at the final velocity is going to be 0. This is the displacement of the truck as it goes up the ramp. So in this case, non-conservative forces, we have initial energy. We're going to have negative work done by friction is equal to my final energy. That initial energy is kinetic. Minus work done is equal to, I do have energy at the end because I went up this hill. I have gravitational energy at the end. So this is going to be my overall non-conservative energy equation. 1/2 mv naught squared minus the force of friction times delta x equals mgh. Now, a couple of things here. I don't know, right now, I don't know what h is. I don't know what delta x is, and I don't know what this force of friction is. So we need to figure those things out. First off, let's do force of friction. Free body diagram for my truck would look like this. Gravity. Normal force is going to be at an angle, and then friction is going to be perpendicular to that. And that normal force is going to be equal to the vertical component of gravity, where this little angle is theta. So the normal force is equal to mg cosine theta. So that helps me solve this part out. My delta x, let's just leave it as delta x. Then the height would be delta x times sine of theta. So here we go, substituting all of that back into my equation. One half v naught squared minus mu times mg cosine theta. That is the force of friction equals the normal force, mg cosine theta, times coefficient of friction, times delta x equals mg delta x sine theta. Now, if we look at this, I know m is known, v naught is known, mu is known, m is known, g is known, theta is known, m is known, g is known, theta is known. The only unknown variable for me here is this delta x. So this is now a solvable equation. I can say, let's get rid of all the highlighting now. So 1/2 mv naught squared equals mg delta x sine theta plus mu mg cosine theta times delta x. Factor out delta x there. 1/2 mv naught squared equals delta x times mg sine theta plus mu mg cosine theta. Divide both sides by that whole expression, and you get delta x equals mv naught squared over 2 times mg sine theta plus mu mg cosine theta. And that's my answer. Yay! Second part of this question says, you need more massive trucks, right? If I wanted it to be more massive trucks, what would happen to that? And if you look at this equation, you can see that the mass of the truck appears in every term. Mass, mass, mass. And so the mass actually cancels. So for part B of this, mass has no effect. It's included in every single term, therefore it cancels out in the long run. So that's this problem. Last one. We got our toy cannon used to project a soft rubber ball. It's compressed a certain amount with a certain spring constant. It moves through a horizontal barrel where there is a frictional force applied. So this one gets really complicated, but I like it. It's a good question. So here are my givens. I'm given the mass of the ball. Don't forget that that's in grams, so you'll need to convert it to kilograms. I'm given the x of the spring. That's, again, in centimeters. You'll need to convert it to meters. I'm given the spring constant, k. I'm given the displacement of the ball through the barrel. Again, that's given in centimeters. You're going to want to convert that. And I'm given this frictional force of 0.0315 newtons in this case. That's given in newtons. This spring constant's given in newtons per meter. So everything needs to be aligned. We need kilograms, we need meters, and newtons all together in this problem. So make sure that you're doing your unit conversions correctly. So leaving the barrel of the cannon, okay, non-conservative forces because of friction. My original energy minus the work done by friction is going to be equal to my final energy. That is spring energy minus work equals kinetic energy. Again, it's horizontal, so gravitational potential energy is not going to be a factor here. So 1/2 kx squared, that's x of the spring, minus the force of friction times delta x of the barrel equals 1/2 mv squared, leaving the barrel. Solve that for v. I get v equals the square root of kx squared minus 2 times the force of friction times delta x of the barrel divided by m. So that's my maximum, or my velocity when I leave the barrel. Now things get fun. Now things get fun because part B says, what is x when at maximum speed? So this is a cool question because the forces in this problem are changing. Remember that as the spring extends, the force that the spring exerts on the ball will decrease because its displacement from equilibrium is decreasing as well. And then the frictional force stays the same. So initially, the instant the ball starts to move, this is what its free body diagram looks like. And I'm going to omit the vertical forces here because they're not relevant. So initially, I have a large spring force and a relatively small frictional force. This is going to cause the ball to accelerate. A second later, right after launch. That frictional force will be smaller. I'm sorry, the spring force will be smaller, but the frictional force will have stayed the same. The net force has now gotten smaller. Still accelerating though. So it's speeding up, speeding up. But at maximum velocity, that's where the ball will stop accelerating. In other words, maximum velocity will happen when the spring force is equal to the frictional force. Now the net force is 0, acceleration 0. We're now moving at our max velocity. So this question is asking, at what point will the spring force be equal to the frictional force? This is saying at this point, the force of the spring is equal to the force of friction. Force of spring is K times X. That's Hooke's law. That was discussed briefly when we talked about spring force in the first place. So that's going to be equal to my frictional force. And so then that X is going to be the frictional force divided by the spring constant there. Again, my frictional force is given, my spring constant is given. So that will be the displacement from equilibrium. So then the delta X will be the equilibrium position, right? So that'll be, in this case, that'll be 4.98 centimeters from start. So there will be our delta X. And then lastly, the maximum speed. So now I'm calculating the velocity at that point. So at that point, I'm just substituting this X here into this equation here. I have an equation that is the velocity is going to be the square root of kx squared minus 2f friction delta xb over m. So square root of kx squared minus 2 force of friction times delta x for this case. So that's going to be x naught minus force of friction over k, all over the mass. This is substitute the answer from B into the answer from A. And we're done. Whoop, whoop. Okay, guys, see you on the next one.